Assalamu alaikum. So let's start our today's lecture in which we are going to complete the remaining part of chapter number 6. So far in chapter number 6 we have studied the construction and working of two famous energy storage elements, capacitors and inductors. And furthermore we have derived the formula for energy of capacitor, and also we have derived the basic formulas of capacitor current and voltage. Next, in the previous lecture, we developed methodology to solve the questions related to capacitor voltage and current, in which voltage or current is given in the form of a waveform. So the idea is to calculate the equation of line between different durations and then use the formula of current if voltage is given, or formula of voltage if current is given, to find the required output waveform. So in this example we are given the waveform of voltage. So I decided to break down the interval from 0 to 4 seconds into three parts: 0 to 1, 1 to 3, and 3 to 4. And hence I figured out three equations of lines from duration 0 to 1, this line, then from duration 1 to 3, this line with negative slope, and then from duration 3 to 4, this line from with positive slope. So here is the working. You can find the equation of line by 2-point formula. So if I want to find the equation of this line, I need 2 points. So one point I can take is region 0, 0, 0, and the other point I can take is 1, 50. And for this line I can take 2 points like 1, 50 and 2, 0, or 1, 50 and 3, minus 50, or 2, 0 and 3, minus 50. So any two set of points will do the job, will be enough to find the equation of line from interval 1 to 3. And for this interval, I can use 2 points like 3, minus 50 and 4, 0. So the equation of lines for the three interval comes out to be this. And next, we have to find the current, for which the capacitor current formula is C dV by dt. I have to differentiate the equation of voltage in each of these intervals and then multiply it by C, and which will result in the value of current. And then simply I can plot the value of current with respect to time axis. So this is from interval 0 to 1. The value of current is 10 milliampere. So I drew a horizontal line with magnitude 10 milliampere, and from interval 1 to 3, horizontal line will be below the time axis with magnitude minus 10, and from interval 3 to 4, it will again be a horizontal line parallel to x-axis with magnitude of 10 milliampere, and beyond 4 Since there is no voltage, there will be no current. Using this strategy, we can find the current of a capacitor and draw its waveform if the waveform of voltage is given and vice versa. Next, we move on to the example 6.5 in which we have to find the energy. It is very simple. Obtain the energy stored in each capacitor. So as you can see, let me amplify the slide. There are two capacitors. One is parallel to the 2 kilo ohm resistor and its value is 2 millifarad, and the other capacitor is in series with 5 kilo ohm resistor and its value is 4 millifarad. As you all know, the formula for energy is half CV square. Here C is the value of capacitor and V is the voltage across the capacitor. So this problem can be solved if we know the voltage across each of these two capacitors. So as you can see, the voltage across 2 millifarad capacitor is the same as the voltage across 2 kilo ohm resistor because both of these elements are parallel to each other. Similarly, voltage across 4 millifarad capacitor will be equal to the voltage across 4 kilo ohm resistor. How? Let's move forward. As we all know, the current source is DC. So under DC operating conditions, capacitor behave as an open circuit. It means it blocks the DC voltage and DC voltage. So we can replace the capacitor by open circuits and then find the open circuit voltages, which will be the voltages across the capacitor. We want to find V1. It's very simple because here is an open circuit, so this 5 kilo ohm resistor is not participating in the circuit. No current will be flowing through it. So these three resistors, so 6 milliampere current source will divide its current between two branches. One branch will consist of 2 kilo ohm resistor in series with 4 kilo ohm resistor, and other branch will be 3 kilo ohm resistor branch. So you can say that 2 kilo ohm resistor plus 4 kilo ohm resistor are in parallel with 3 kilo ohm. Hence, we can use current division rule to find the current through this 2 kilo ohm resistor, because if we are able to find the current through this 2 kilo ohm resistor, then we can find the voltage of this resistor by using Ohm's law, which is equal to IR. So we want to find the current through this resistor. So it is, this resistor is a part of this whole branch, and this whole branch is in parallel with 3 kilo ohm resistor. So if we want to find the current through 2 kilo ohm resistor, the formula will be 3 kilo ohm should go in the numerator divided by the total resistance, which is 3 plus 4 plus 2, and it comes out to 9. 3 by 9 multiplied by total current, which and the result is 2 milliampere. So the current through this 2 kilo ohm resistor will be 2 milliampere, and the voltage across 2 kilo ohm resistor will be 1, and that will be equal to 4 volts. Hence the voltage across this capacitor will be 4 volt. Similarly, the voltage across these terminals will be equal to voltage across 4 kilo ohm resistor, and that will be 4 kilo ohm multiplied by 2 million here, and that comes out to be 8 volt. So now we know the voltages across each capacitor, hence energy can be calculated. W1, which is the energy stored in the capacitor 1, formula is half C1 V1 square. In the values, it comes out to be 16 millijoule, and for the other capacitor, formula will be half T2 V2 square, and by putting the values, the result comes out to be 28 joule. So it's very easy. You just have to find the voltage across the capacitor. And these voltages can be found by simple circuit analysis. Next we must know what is the formula for the finding the equivalent capacitance if two or more capacitors are connected in parallel. So if two or more capacitors like this are connected in parallel, the equivalent capacitance will come out to be the individual algebraic sum of the capacitance. Means capacitors in parallel. When capacitors are connected in parallel, the equivalent capacitors can be found similarly as the resistors are connected in series. So if capacitors are connected in parallel, their capacitance adds up, like the resistors are connected in series. It's very simple. So when the resistors are connected in series, they behave as, and if we want to find the equivalent resistance, their resistance decreases, their capacitance decreases, and it comes out to be the same as the resistors are connected in parallel. The formulas are on the same pattern. So you just have to keep in mind that when capacitors are connected in parallel and we have to find the equivalent capacitance, we should use the formula to find the equivalent which we use to find the resistance equivalent resistance when two or more resistors are connected in series, and when resistors are connected in series and we want to find the equivalent capacitance, we should use the formula which we used to find the equivalent resistance when resistors were connected in parallel. So the formulas are just simply flipped. Like this, in this example, you have to find the equivalent capacitance between terminals A and B. In the chapter 2, you saw that instead of capacitors, there were resistors, and you were able to find the equivalent resistance. Here, the only difference is that resistors are replaced by capacitors, and we have to find the equivalent capacitance between terminals A and B. So let's start. 20 microfarad and 5 microfarad capacitors are in series, hence we will use the formula which we use to find the equivalent resistance when two resistors are connected in parallel. So hence the result will be, for this branch, the equivalent capacitance will be 20 multiplied by 500 divided by 20 plus 5 means 100 divided by 25, and the result will be 4 microfarad. Then 4 microfarad will be in parallel with 6 microfarad, and the result will be 4 plus 6, and it will come out to be 10, and then 10 and 20 will be in parallel, and the result will come out to be 30, and then 30 and 60 will be in series, and the result will come out to be 30 multiplied by 60 divided by 30 plus 60, and 1800 divided by 90, and the result will be 20 microfarad. These are the steps. You can easily verify the steps. Next, we must understand the basic shape, construction, and working of an inductor. In inductor, the energy is stored between the magnetic field, while in the capacitor, the energy was stored in the electric field. So this is the basic shape of an inductor. It resembles a coil or a wire wounded into circular rings. So an inductor consists of a coil of conducting wire. ज्यादातर हमने देखा है कि ये जो कॉयल है इसके बिटवीन ये कोर मटेरियल होता है. अगर मटेरियल ना हो तो एयर को एयर होती है और एयर की आपको पता है रिलक्टेंस बहुत ज्यादा होती है. इसलिए हम कोई ना कोई और मटेरियल यूज करते हैं ताकि जो फ्लक्स है वो जो जनरेट हो रहा है उसको पास करने के लिए एक लेस रिलक्टिव पाथ अवेलेबल हो जाए. एयर की रिलक्टेंस बहुत ज्यादा होती है. लेट्स से अगर हमने इस कॉयल को कुछ करंट प्रोवाइड किया है तो इसमें से एक मैग्नेटिक फील्ड लाइन पैदा हो जाएगी और हम चाहते हैं कि वो मैग्नेटिक फील्ड लाइन किसी और कॉयल के साथ भी एक्ट करे. तो हमें उन दोनों कॉयल को एक ही कोर के ऊपर कनेक्ट करना पड़ेगा ताकि फ्लक्स लाइन इजीली एक कॉयल से दूसरे कॉयल तक पास कर जाए. जैसे कि ट्रांसफार्मर होता है, प्राइमरी वाइंडिंग होती है और फिर सेकेंडरी वाइंडिंग होती है और उन दोनों को एक ही कोर के ऊपर काउंट किया जाता है ताकि फ्लक्स को एक इजी पाथ प्राइमरी वाइंडिंग से सेकेंडरी वाइंडिंग तक मिलता रहे. So reluctance is similar to resistance. In resistive circuits, resistance is the opposition to the flow of current, hence the reluctance will be opposition to the flow of flux lines. So usually we want a less reluctive material like silicon, steel, and other metals. So L is the length of length of the core, and A is the area of the core, N is the number of turns of the coil. Okay, now uh, move towards the next slide. So we have studied the basic construction of an inductor. It is just a conducting wire wound into different number of turns, and the core is put there to increase the connectivity of flux from one coil to another coil or one coil to another metal element or whatever the requirements will be. So what is inductance? Inductance is opposition to change in current, just like resistance. Resistance is opposition to the flow of current. So here is a little difference. Inductance is opposition to change in current, and inductors are components that are manufactured to oppose change in current. Suppose that a circuit has an inductor connected in it, and a certain current is flowing through the inductor, and suddenly you have decided to increase or decrease the current, then the inductor will oppose this idea and will try to keep the value of its initial current. Let's say initially current was flowing 2 milliampere and you want to increase the current to 2.5 milliampere. Then the inductor will do this change and try to bring the current to 2 milliampere. But eventually, since external energy is being applied, the inductor will lose its fight or lose, or you can say the current in the circuit will change from 2 milliampere to 2.5 milliampere due to the external source, which is way more powerful than the will of inductor. It means if we want to suddenly change the amount of current in an inductor, it will first poses this idea and then it will submit to the will of the external energy source. Same like capacitor, you cannot change the voltage of the capacitor suddenly, but after fighting for some time, the voltage of the capacitor can be changed because the external energy source is way more powerful than the uh, opposition offered by the capacitor. So I can summarize these 2 points as this: capacitor opposes the sudden change in its voltage, while the inductor opposes the sudden change in its current. Why is that? Because the formula for the voltage across the inductor is L di by dt. Now let's say what does happen when a DC source is applied to the capacitor, to the inductor. As you can see in the inductor, there is rate of change of current, and we all know in DC current source or DC voltage source, the value of current does not change with time. So the answer of di by dt will be equal to 0 and the voltage across the capacitor will be 0. And if the voltage across the inductor is 0, sorry inductor, so if the voltage across the inductor is 0, it means inductor behaves as a short circuit in case of DC power supply. So again we can use this equation to know why the inductor opposes sudden change in current, because let's say current is flowing 2 milliampere and suddenly within no time it tries to change from 2 milliampere to 2.5 milliampere. The slope of the current line will be infinity, means di by dt will be infinity, and hence the voltage across the inductor should be infinity, which is not practically possible. Again, I summarize this. Let's see the current flowing through the inductor is 2 milliampere, and suddenly you want to increase the let me use a drawing board. I cannot find. So this is 2 milliampere current flowing in the inductor, and suddenly you want to increase the current to 2.5 milliampere. This was 2 milliampere line. Uh, Sorry, my drawing is not that good, but you have got the idea. So the slope of this jump line is infinity, hence the voltage of the inductor should be infinity as well, which is not practically possible. So now we have to find the mathematical formula for the inductance, which is equal to L is equal to N square mu A over L, where L capital letter for stands for inductance, N stands for number of turns of the coil, mu is the permeability of the core material. Permeability of the core material, which is defined as the ability of the core to allow the magnetic flux lines through itself. The product of mu r and mu naught is uh, mu is the product of mu naught and mu r, where mu naught is the permeability of free space means air, and mu r is the relative permeability. So the product of mu naught and mu r should be greater and greater for a core material to be more permeable. Okay. L is the length of the core, A is the area of cross section of the core, and mu is the permeability of the core. So inductance increases. Inductance, yeah, which is opposition to the change in current, increases by increasing the length of, by decreasing the length of, and it increases by increasing the number of turns. It increases by increasing the cross section area of the core. It also increases by increasing permeability. So let's move forward. So these are the three symbols for different type of inductors. Air core, for air core we use simple this sim, symbol in which where the current enters and the positive terminal of the inductor and is at the negative. For iron core, you just have to draw two parallel lines next to the coil to show that an iron core is used. And for variable iron core, an arrow is placed crossing the coil and the core parallel lines. And these three pictures correspond to the this picture corresponds to the air core inductor, this picture corresponds to the iron core inductor, as is in the case of transformer, and this is the picture for variable iron core inductor. Now we have to see what is the current and voltage relationship. As I already mentioned, the voltage across the inductor is L di by dt. From this formula, we can find the formula of the current through the inductor just by rearranging this voltage equation. So separating the differentials by the famous technique, we can get this form, and integrating both sides, we can find the current through the inductor. So di, to integrate di, it will result in I, and when we apply integration on the left, on the right hand side, one over L is constant, it will come outside of the integration. And as we all know, in case of capacitor, we took the interval from minus infinity to t. Same interval will be taken in this case as well. Next, we can resolve this interval uh, into two intervals, minus infinity to t should be equal to minus infinity to t plus, or you can say just before performing the experiment, plus minus infinity to t, and we have to put dt over here and over here as well. The answer of this integration will be, sorry, I have uh, misplaced the limits, minus infinity to t and then t plus and then t plus to t. Of course, we have to put vt dt over here and over here as well. The answer of this integration will be the initial value of current stored in the inductor before connecting into another circuit, or you can say before performing the experiment. Let's say your colleague has performed an experiment, and after performing an experiment, you happen to come on the same table and you use an inductor which was already in the that inductor now have some initial value L2 of current. So minus 20 to T plus means the current present in the inductor way before performing the experiment, and we will accommodate it by calling it IT naught, means initial value of current stored in the inductor, and the answer of this integration we can find T naught is equal to T plus, and it is also equal to T negative. T naught is usually taken to be the origin, means T naught is equal to 0. Just before 0 means T plus, and just after 0 means T negative, and the current of the inductor just before 0 and just after 0 same. Hence, we can put 0 over here instead of T naught to find the overall current through the inductor. Means initial current plus, if the experiment starts at T naught is equal to 0 to T, means starts at T is equal to 0 second and goes ends at T is equal to T second, means T may be 5 seconds, 10 seconds, or whatever the case may be. Next, how can we find the power? So in the inductor, same procedure as we followed in the finding the power through the power in the capacitor. VI is the general formula. Instead of V, we can write LD as the dt and I is I. So energy is equal to, as you all know, P dt. Again, limit we have to put minus V to T. Instead of P, we can put this value, and it happens to come out to be this, because inductance is constant and it is thrown out of the integration, and dt is cancelled by dt, and now we have I di. The differentials have switched from time variable to current variable, and we have IDT, hence the limits will also change. Instead of minus 20, here will be I at minus 20, instead of T, it will be I at time is equal to. So integration of IDT is equal to I square by 2, and we have to apply the limits, upper limit minus lower limit, and the formula becomes this. And now, as we all know, current at minus 20 is always equal to 0, as the voltage at minus 20 was equal to 0, because current at minus 20 means the current in the capacitor long before connecting to the any active circuit, which will be equal to 0, because if there was some current in the capacitor, it will be diffused if it is given an approximate for a long time. Hence, since I minus infinity is equal to 0, this component comes out to 0, and the energy stored in the will be equal to half Li square t, and we draw the, for simple, we draw the variable with which the energy is changing. Simply you can write W is equal to half Li square. Some important properties we have to discuss. I have discussed them earlier in this lecture, but again for revision I can repeat. Inductor acts like a short circuit to DC, because, as I already discussed, the current of a DC voltage source or current doesn't change with time, and the answer of the IPDT is equal to 0. and the voltage across the bulb is the short circuit. The current through an inductor cannot change instantaneously or suddenly. That's also I have uh, discussed. So the change in current as drawn in figure A is allowed and not as drawn in figure B, because in figure A the current is changing through the inductor with some finite slope. The slope of this change, the slope of this line is not infinite, which is di by dt by the way. It has some slope, and the voltage across the inductor will not be infinite. While in this case, at time t is equal to 0, time t is equal to 0, the voltage suddenly change and the slope of this vertical line is infinity and the voltage across the vector should be infinity, which is really not possible. Hence, the sudden change of current through the inductor is not possible. Inductor will oppose this change as long as it can. Similarly, this is the summary for all these three elements for resistor. This is the formula of voltage across the resistor by Ohm law. This is the formula for the current capacitor. This is the formula for the voltage, and this is the formula for the current. And for inductor, as we stated now, the voltage is L di by dt, and the current is this. So now we have to find the current through voltage or current, voltage through the inductor or current, voltage cross the inductor or current through the inductor. The current is given, we have voltage and energy and voltage, current or. So in this example, the current through point 1 Henry inductor is this, it is 10 t e raised to minus 5t. Here, find the voltage across the inductor, A, and the energy stored. As you all know, the voltage across the inductor is burned by this equation, P is equal to L di by dt, and value of inductance, capital letter, for L is equal to 0.1 Henry, this value here, and take the derivative of current. Derivative of current will be equal to by, as you all know, product rule will be applied here because there are two functions t and e raised to minus t. So the result, applying the product for derivation for voltage term, energy stored will be of Li square, that is already given, I is already given, so I take the square of I. Now just by putting value, if someone asks what will be the voltage at t is equal to 5 seconds, you have to put t, you have to put 5 instead of in place of in place of 5. So again, if someone asks what is the energy stored in the vector at t is equal to 5 seconds, so 5 here in place of t. To find the current through the 500 inductor is the voltage graph. Now the voltage is given. Find the current. We know the formula. I is equal to this. T is, but there are two intervals also. The voltage is divided into two intervals. For t greater than 0, it is 30t square, and for less than t, uh, t less than 0, it is 0. Means voltage is positive because t less than 0 is 0. For t greater than 0, it is 30 t square. So big deal. Just put the value of Vt here, 30 t square dt, shell value of current is not given, it is assumed to be 0, and current becomes this. The power is equal to Vi, V is given 30 t square, we multiply it by I, which comes out to 2 t square, it becomes 60 t raised to the power 5, and then energy can be found by this equation, in which we have the limits 0 to 5, because for that there is no take for the capacitors. We have to take a time interval from 0 to 5 seconds as given in the question. The alternative way of finding energy is what Li square, as you all know. Li square. So I came out to be 2 into 2 raised by 3. But 5 means that in place of t, 5 cube is equal to 125, 125 into 2 is equal to 50, and then you have to take its square and put all the values in it as well. Found by this. You can use many ways. This consider a circuit in figure 6.27. Under DC conditions, find I, VC, and IL. It is an hybrid circuit now. It contains both of the energy storing elements. And we have to find the current I, this current generated by the 12-volt battery. VC is the voltage of the capacitor, and IL. The vector energy storage, energy stored in bus conductor, we have to find them. And what should be our technique? First of all, note that it is DC power supply. So, capacitor will be open circuit and inductor will be short circuit. So, under DC condition of circuit, our circuit will look like this. Inductor is short circuit and capacitor. So now, as you can all see, this whole common is not a part of the active circuit. 1 ohm and 5 become comes connected in series. So if we want to find the current I, we can find it easily. It should be equal to total voltage over total resistance. The voltage 12 volt, total resistance 6 ohm, 12 12. I is equal to 2 ampere, and this I, as you can all see, current generated by this voltage source is also flowing through this short circuit where inductor was connected, and I is equal to IL, and you can all see because this branch doesn't carry any conductor, 1 ohm resistor and 5 ohms are in series. if ये दोनों सीरीज में हो जाएंगी तो करंट फाइंड करना है. Current generated by the source same as the current factor. I is equal to IL. We have found I and IL. Now we have the VC. As you can all see, जैसा कि आप सब देख सकते हैं, वोल्टेज क्रॉस बस के क्रॉस जो वोल्टेज है वही होंगे 5 ohm resistor और resistor is in parallel to 5 ohm. 5 किलो ओम के रेजिस्टर के जो वोल्टेज होंगे वो होंगे 5 multiplied by the current to 5 resistor which is equal to IL I to so voltage or the resistor will be equal to 5 into I 5 to 2 is equal to 10. Okay, we have found the VC as well. Next step was to find as stored in pressure, which is half CVC square, very easy, and as stored in inductance half LI square. Series and parallel pressure, same. Series and parallel inductors. When inductors are connected in series or parallel, then the formula to find the equivalent inductance for series connected inductor or for parallel connected inductor is in the same lines to the formulas which we use to find the equivalent resistance when resistors are connected in series or in parallel. So if, as you can see, L1, L2, L3 up to Ln inductors are connected in series, then the equivalent inductance will be equal to simple the definition of their individual values. And the voltage across each inductor will be added, find the total voltage, and it can be shown by KVL. Similarly, when inductors are connected in parallel, the equivalent will be found by this formula, which is the same line on the same line as the formula used to find the equivalent resistance and two or more. Formulas for finding equivalent resistances or resistances or inductance are same, or you can say are on the same line. But for the rest, these formulas are flipped. So here is the summary. You can give 2 minutes to this chart. It's very helpful. So find the equivalent is very easy. 12 plus 10 plus 12 plus 20, 42, 42. 2 parallel with 7. Then the result of 7 in parallel with 44 will be added in 4 and 8. So 7 and 44 in parallel. That will be 7 multiplied by 44 divided by 7 plus 44, 51 means 44 multiplied by 7 is equal to 44 multiplied by 7 divided by 4 plus this the number will be 6 and 6 plus 8 plus 4. Very easy. Some more examples are to be solved. Let's solve them and finish this chapter. This is very famous example, very useful example for understanding the behavior of inductors when connected to a time varying power supply. For the circuit in figure 6.33, total current IT, this current IT is 4 into 2 minus e raised power minus 10. If I2 is current, I20 means initial value of current flowing through 12 Henry inductor is minus 1 milliampere. Find I10 means find the initial value of current flowing through 4 Henry inductor. Also find total voltage, which should be put here. Also find the voltage across 2 Henry inductor. 1, 2. Also find the voltage across 12 Henry inductor. Part C, you have to find the current through 4 Henry inductor and for current through 12 Henry inductor. Right. So what should be our approach? We are only given this and we have to find initial value of current 4 Henry inductor. It's very easy as first of all you have to see that you can apply KCL at this point. At this node you can apply the KCL. There will be I is that I1 and I2 are the two leaving current. Equation will be I will be equal to I1 plus I2, and we can modify this equation for initial value of problem. So hence you can write it I of 0, I1 of 0 plus I2 of 0. Because whether it's initial current or some other current, the KCL cannot change. It will remain like this. Just we have to put the value of E, modify it according to our requirement. So in this equation we have put 0 instead of t. Here again it was I of t. We have 0 instead of t. Here again it was I2 of t. We want to find the initial value of current through 4 Henry inductor, which is I1 of 0. So I of 0, we know the value I given. 1 Henry I1 of 0 we can find, put 0 in this equation. So that will be 4 into 2 minus e raised power minus 0. E raised power minus 0 will result in 1. So 4 into 2 minus 1 and plus 4 million. The values 4 instead of I of 0 put 4 million there minus sign will come as it is, and then put minus instead of I2. Hence I1 of 5. Part 1 is solved. Now we want to find the total voltage. It should be connected here. For this, we have to find the total inductance of this entire system. It's very easy. 4 and 12 in parallel. The result will be equal to P into series. The total voltage, if you want to find, you have to use the inductance, and this should be multiplied by di by dt. Then you have total current that instead of in place of L equivalent, we should put 5, and then you have to find the derivative of I with respect to t. 4 will come out of the derivation, and derivative of 2 e to the minus 10 is equal to this, which comes out to be 200 e to the minus 10. We have found the total voltages should be 40 200 e to the minus 10. Why we know? Because the current was in. So now next two voltages are very easy to find. If you know the total voltages, you can apply KVL to find the other two voltages. So now we find V1T. The voltage was 2 Henry inductor, and we know also know the current through 2 Henry inductor same as the total current, which is given in the question. So V1T is equal to 2 to di by dt, which comes out to be 80 e raised to minus 10. So you know the V1T, you also know VTV, now V2T very. The dates are that V of T is equal to V1T plus V1 to minus V2T, it should be equal to V minus V1. V was equal to 200 e raised to minus 10 minus V1T, which was equal to 80 e raised to minus 10. Now for part C, you have to find the currents I1T and I2T. I1T, very easy, as you all know the formula. I1T is the current through 4 Henry inductor 1 by L. Instead of L, you can put 4 Henry. Integration from 0 to T plus initial value of I1 V2 dt. So V2 we have found already, which was equal to 120 to the minus 10 T 120 comes out of the integration value constant. And initial value of I1 was equal to 5, we have put 5 here. Then integrated after putting values. I1 T comes out to be 8 e raised to a minus e raised to the minus 10. So I2T you can find by this equation again. Here you know the I, which is this, and now you have found the I1. So I2, you can find the I1 by just calculating I minus I2. Or you can use this integration formula, whatever suits the best. So in this way, uh, we can deal the hybrid circuit which contain both inductors and. So with this, our chapter 6 is over, which was about this elements. In this sector, we learned how to calculate the energy stored in capacitor, it is how to find the voltage of capacitor if current is given, how to find the current of capacitor is given. Similarly, how to find the equivalent capacitance if capacitors are connected in series or capacitors are connected in parallel. Similarly, in case of inductor, we do the same phenomena. We were able to find the voltage through inductor if current was given and current through inductor was given. Same. Similarly, we were able to find the equivalent inductance and if inductors were connected. series, or if they were connected in parallel. And then at the end, we were able to find the different voltages and currents of the circuit in both the vectors tested at the same time, which are called hybrids. I hope you have understood what I was intending